did the necessary setup about the curl in the previous video, so now it's time for us to talk about Stokes' theorem. So here is Stokes' theorem. Let S be a piecewise smooth oriented surface with piecewise smooth boundary C. Here's a vector field F. You know, normal, continuous first partial derivatives, okay, an open region containing S. Then the circulation around C of F, counterclockwise, equals the integral, the double integral of the curl vector field over S. So the integral of C, the circulation around C, this is the boundary of the surface here, is equal to the double integral of the curl over the surface itself. Let me just draw a picture here. Let me draw a picture. So let's say that our surface here is, you know, this surface right here, top hemisphere, and it has this boundary right here. This is the boundary. So S is this surface up here. C is just this boundary down here. So what Stokes' theorem is saying is that the integral along C of f dot dr here, integral of f along the boundary, is exactly equal to the double integral over S of the curl up here. So somehow this is equal to this. And so one thing that I want to emphasize here is that this should feel very, very similar to the circulation curl version of Green's theorem. So, you know, this and this, compare them. They are very, very similar. So we have, you know, the region R in the plane is bounded by C in the circulation curl version of Green's theorem. Region S in three-dimensional space is a surface that again has C as a boundary. We have a vector field F here. And so then the circulation around C of F, the circulation of F around C, I just interchanged the order of those words, counterclockwise, equals the, in this case, this is the double integral, and this is also the double integral here of the curl of F in Stokes' theorem. In the Green's theorem, it was the K component, the Z component of the curl of F here. So really what's going on is that Stokes' theorem is the way that you would kick up, if you take Green's theorem in the plane and kick it up to 3 dimensions for more interesting surfaces like this one, you end up with Stokes' theorem. And so in the next couple of videos, we'll be working on verifying Stokes' theorem, applying Stokes' theorem, stuff like that.